Today in class, we looked at resolution, which told us how many digits we could record for a measurement based on the measuring device. So for example, we looked at this graduated cylinder, and because this graduated cylinder is marked to the 10th of a milliliter, you're able to estimate the 100th of a milliliter. And so you might record a value of like 9.51 milliliters as a volume coming off this. You can go to the 100th of a milliliter. If you compare that to this larger graduated cylinder, you had the same water in here. This graduated cylinder is only marked to the nearest milliliter. Therefore, it has a lower resolution, and we can only go to the 10th of a milliliter. And so that same amount of water would have to be marked as being 9.5 milliliters. We can't claim to know that 100th place with a lower resolution device. Now these numbers that we're recording here are known as significant figures. So we call these significant figures. And how many significant figures you get in any measurement is based on the resolution of the measuring device. However, there's another reason why this is important. It tells us what we can report, but it also, the significant figures will also limit the number of digits you can report for any calculation you do that relies on that data. So they limit the digits you can record or report as the answer for any calculation based on those measurements. And that's what we want to look at in this video. So as you might imagine, we have 3 significant figures here, but only 2 here. Any calculations we do with these are going to be limited by that number of digits. So what I want to start with is at the end of the class, for most of the classes, I drew a line on the board. And we put a meter stick up and used it to measure, but the meter stick only had 2 marks, 0 and 1 meter. That meant we could only estimate the measurement to the nearest 10th of a meter. And most of the class said it was about 0.4 meters. We had a few people say 0.3, a few people say 0.5, which makes sense because we know our last digit from our measuring device is a little bit uncertain. And we say it actually has an uncertainty, we assume, of 0.1 meter because 1 in that last digit. And so another way of thinking of this is that line is somewhere between 0.3 and 0.5 meters long, although our best guess is that it's 0.4 meters. So let's think about how this would come into play if we were doing a calculation. Assume we were going to make a square with each side equal to the size of that line. So they would both be 0.4 with a little bit of uncertainty. Could be 0.3, could be 0.5. Now, if we wanted to know the area of that square, we would of course simply multiply the 2 sides. So we'd say 0.4 times 0.4, and if you put that in your calculator, you get 0.16. Okay? But the problem is this answer has 2 digits. The data we're relying on only has 1 digit, one of these significant figures we're talking about, and therefore our answer can only have 1 significant figure itself. So we're going to round this to 1 digit, which would be the 10th place. Because there's a 6 here, we're going to round up, and so this becomes 0.2. That has to be our answer. Now recall, whenever we report something with these significant figures, we know there's some uncertainty there. We assume plus or minus 1 in that last place, so plus or minus 0.1 here. And so what we're really saying is the true area is someplace between 0.1 and 0.3, and the unit here would be centimeters squared because we multiplied centimeters by centimeters. Actually, these should be, meters squared. We're in meters up here. So we've got a range of possible values. Now, does this make sense though? Well, let's think about the possibilities. We're assuming it's 0.4, but we know it might really be as small as 0.3 times 0.3 at the low end. Well, if you multiply 0.3 by 0.3, you get 0.09, pretty close to our low end of our range of 0.1. On the other side, maybe it's really as great as 0.5. So if it's really 0.5 times 0.5, well then our area is 0.25, fairly close to the 0.3 on our high end of the range. So you can see what the Sig Figs are doing for us is they're accounting for the uncertainty when we do a calculation and telling us how much uncertainty there is in our answer. If we'd left our answer as 0.16, that would have implied that the true value was somewhere between 0.15 and 0.17 meters squared. That doesn't accurately represent the true range. 0.1 to 0.3 does do a very good job of accurately representing how much uncertainty there is in our values. So, the rule here that you need to apply: when you multiply or divide, and that's 90% of the calculations you're going to do, your answer can only have as many Sig Figs as the value you relied upon with the fewest or least Sig Figs. And Sig Figs there is just short for significant figures. Now, both of our numbers had 1 Sig Fig, so our answer had 1 Sig Fig. But if this had 1 Sig Fig and this had, say, 8, the answer would be limited to 1 Sig Fig, the least number of any of the data you started with. So let's just look at one example problem to think through how this might work. So here we've got an example. Suppose you travel 2,222 miles in 2 hours. And the question is, what was your average speed in miles per hour? Okay. So, when we look at this, in order to get this, we would look at how many miles did we travel and how many hours did that require. If you look at your units, you can see we're going to get an answer that's miles over hours, miles per hour. And when we do the math, it ends up being 1,111 miles per hour. That would be our assumption. But now let's think about Sig Figs. We had 2 pieces of data that we started with. This one had 4 digits. This one only had 1. How many digits can we then have in our answer? We're limited by the lowest number of any of the data we relied upon. We only have 1 Sig Fig. Therefore, we have to say we think we were going about 1,000 miles per hour. I'm going to use MPH here as another way of abbreviating miles per hour. Now, what is the implied range here then? It's plus or minus 1 in our last digit that we claim to know. Well, the only digit we're claiming to know is this one. So we're really saying that the true speed could be anywhere from 0 to 2,000 miles per hour. There's a huge amount of uncertainty there. Why are we so uncertain? Well, the reason we're so uncertain is because our time measurement has a huge amount of uncertainty, right? We said 2 hours. That implies that we don't really know exactly how many hours it was, right? Our last digit is a little uncertain. We're saying it's anywhere from 1 to 3 hours if we only report 2 hours. If we knew better, we should have said so. We should have said 2.0 hours, but we didn't. Maybe we were measuring with a sundial. For whatever reason, we don't know very well how long this took. So if you think about it, if it really did take only 1 hour, and we traveled 2,222 miles, well, we were going 2,222 miles per hour then, right? Fairly consistent with the high end of our range up there. Conversely, if it turned out that it really was 3 hours, we were going a heck of a lot slower than we thought. Not actually 0, but slower than 1,000 miles per hour. So quite a bit slower than the value we initially thought it was. Okay. So you can see hopefully how the uncertainty in the original measurement carries through and gives you a range in the answer. Now you could always do these calculations twice and figure out the range, but what Sig Figs do is they let you not have to do that. If you follow these rules, you'll get a reasonable range without having to run the calculation multiple times.